use Gauss's law to calculate the field of a charged conducting sphere as depicted in this diagram. We place a total charge Q on the sphere, and of course that charge will all run to the surface and distribute itself uniformly. This is due to the mutual repulsion between these individual charges. We want to calculate the electric field at all points in space, namely outside the conducting sphere, at the surface of the conducting sphere, and internal to the conducting sphere, again using Gauss's law. So our assumptions are that the charge is uniformly distributed on the surface of the sphere. And this means that whatever the electric field is out here, and we assume that it points radially, and its magnitude only depends upon the distance from the surface of the sphere. Because of this, I want to take my Gaussian surface to reflect the symmetry of the system. So I'm going to take it to be a sphere of radius r, where r is an arbitrary value, but centered on the conducting sphere. So now I'm ready to begin. So for r greater than the radius of the conducting sphere, the enclosed charge just has to be q, and E is uniform, radial, and perpendicular to the Gaussian surface. So E dot dA is simply E times 4 pi r squared, and this, of course, is the area of my Gaussian surface, and that by Gauss's law has to be Q over epsilon naught, and I end up with the result that the magnitude of the electric field is Q over 4 pi epsilon naught r squared when I'm outside the radius of the conducting sphere. The direction of this electric field, of course, is radial. When I'm at the surface of the sphere, I get the same expression, but I simply replace lowercase r by the radius of the sphere, uppercase R. For r less than the radius of the conducting sphere, I get the same expression on the left-hand side. Nothing has changed with the symmetry of the electric field, but the enclosed charge now will be 0 because all the charge again is at the surface, and from that I surmise that the electric field inside this conductor is equal to 0. And finally, if I go back and look at the solution, I note that this electric field is the electric field of a point charge that is centered on the conducting sphere. So the electric field outside of this conductor behaves as if all this positive charge were placed at its center. Of course, there is no positive charge at the center, but that's how the electric field behaves. When I'm inside the conductor, however, the electric field abruptly drops to 0, as depicted in this diagram. As I get closer and closer to the surface of the sphere, the electric field grows and then abruptly drops to 0 when I reach the radius.